You see it goes left to right, expected airflow, component details, modified board layout, validate component placement, component temperature, startup, fan failure, fine tune, configuration instructions. And similarly, just like those things are what do you call, here it is as electrical and software, the mechanical point saying overall chassis size, plenums and vents. Plenum means the low pressure area is called a plenum chamber, where you try to pull things. CAD files, percentage open areas, filter selection, EMI mitigation, very critical here. This is what I was telling you, percentage of open areas. While the cabinet itself may be big, meaning you have say some 450 mm by 450 mm cross section, the actual spacing for the air to move will barely be about 20%. Again coming back, if you have a vent itself may be about 100 mm high and 400 mm wide, and you usually have some grill or something about it. So, that is where the filter comes. You cannot ignore a filter even on the outlet side. You know why? You do not want things to enter from the wrong this thing, including whether you like it or not. Several other living beings also live with us. So, and they do not abandon ship. A sinking, there is no sinking ship which these rats abandon. They live there because they seem to enjoy chewing through the cables. Then you see here, most important is the mechanical design, by which me being what you call product designer, and talk about physical and mechanical design, where we finalize the vents, grills, filter, fan placement, plenum height, surface finishes, finally hardware design, validate deployment instructions, usage and service instructions. Very rarely anything is straight away wrong. So, all these inputs, for example, inputs from the top here, from the electrical, same thing, inputs from the bottom comes to cooling requirements, initial system specification. This is your scene prototyping the thermal analysis, then detailed thermal design, device temperatures and so on. So, probe design envelope, failure scenarios, elevated temperatures, elevations, this is critical. That is where I told you, in case you have a fully closed system, one failure leads to other. So, we have build and test the physical mock-up, validate thermal model. So, this design validation of the thermal model also, thermal design validation is very important, and final thermal, this comes to the thing, validate acoustics operation at ambient temperature, you have seen this here, and altitude. So, acoustics and operation and thermal temperature and flow, survivability under failure, thermal controller, burn-in, agency pre-qualifying tests, these are not easy. So, I will thank the what do you call the presenters who have made this slide. I suggest you kindly go to this their website, engineering airflow degree controls, and then maybe you can get in touch with them, because for every item they have given reasonable tutorial type things. Now, coming back to the next slide. We come to a very beautiful concept. I do not know actually how it works, but then we all of us do like that. This is now a very talked about and common thing, easier said than done, saying why can't we have concurrent design, saying talk with the other departments. With those people are not yet familiar with it, and then those youngsters, we have two ways of doing things. One is called over the wall design, saying somebody who is an expert decides what is good for the circuit board, and a reasonable thing he does, and makes a PCB or makes a circuit design, and then passes on to the next person, and the wall here refers to saying you just push it over the wall, that person worries about the other thing, his field, and eventually it comes to, in the end it comes to the user, and then suddenly we find that what was started then is not valid anymore now. So, we have problems. So, these days instead what people are saying is, if you avoid this type of what do you call specializing in that area, and somehow all of you work together, saying it is not about too many cooks spoiling the broth. Imagine there is a cutter who has to chop the vegetables and put them inside, and then imagine there is somebody who is preparing the stock. I do not know how stock is prepared, and then there is, imagine, the kitchen equipment person who makes the kitchen equipment, and finally the master cook. All of these have to remember under what conditions the thing is being made. So, if in the final thing all the people come and keep on, no, everybody adds salt thinking the other fellow hasn't added, you know what happens to the soup. Otherwise, concurrent thermal is very much valid, saying right from the initial stage, people all, it is not like our Friday meetings. Friday meetings are still something to be desired, because you end up with so many bystanders and passengers who probably come for the snacks. So, the thing is, the person who is thinking about it, he should know, here it looks like a large, this whole system has been designed for a large rack, and then you see here this sub rack probably is a DIN that usual so called we call it a 19-inch sub rack. But you see, very important thing, you see there is a inlet here at the bottom. It looks a little like, I do not know whether it is a shadow or actually it is there, it looks like intentionally they have left an opening which is a multiple of the U's. This looks a little like a very odd 4U, normally we have 3U, and most of these the equipment you come across these, there are 1 or 2U, 3U is fairly standard, because the plugins, plug-in PCBs have been standardized with a Euro card, which is typically 100 mm high. If you have a 100 mm high by 150, 160 mm depth, you end up with a 3U. So, usually it is very easy for us to add a inlet from the other side. Same thing in reverse, no? So, you have all these cards, and then these look like card pullers. It is a card lock, you open it and card pullers, and then we end up with a beautiful, you have seen here, you have air inlet, and then air is going up, and then they very conveniently, maybe due to simulation, no, it just shows how well everything is cool and blue. This you have heard, I need not tell faster time, because avoid costly redesigns. Directly on design geometry, saying you fix up on a design geometry, so parallelly somebody works on the both the electrical, especially electrical parasitics. It looks like, if you look at the whole thing, the well understood part is a circuit design. Okay, even you have analog digital mixed mode analysis available at the circuit design stage. But what is even the next level in the board design level also, no, some part of thing can be managed, but the moment it goes into a larger system, we have a little problem. It is not as if it is surmountable, remember it is working. My phone at very inopportune moments, my phone works. I do not want it to ring, I am sure it will ring one of these things. That very fact shows that the tremendous amount of support from this has been done well, except that they have achieved this level after a little bit of having to do redesigns. Most of the things what you have in place are probably the third time around things are done. Even now occasionally you see for somebody taking what you call a pedestal fan and trying to cool things. It is like Over here in the tropics, whenever you see a big truck, usually they remove there is a bonnet portion, and then there is a small slider, they remove it, they run it in the open condition. Even if it blocks the driver's what you call immediate view will be reduced. Even then, that is the only way to run large trucks under our oppressive heat. For us, if you go on tar roads and those thermals and all that, ambient just at the input may reach beyond 45 degrees, and I have known places where it is a little higher also. So, redesigns can be avoided. Design 2, more important is we have all these various standards. NEMA Indol electrical manufacturers, then you have the DIN standards, then you have the various types of, I do not know the expansion, but various industry standards where things are automatically interchangeable. If something fails, somebody else will take over. It has nothing to do with the contract, it is about maintaining. So, this is easy. I will just try to breeze through, because this is not the lecture is about. So, we have this saying, build a model and then discretize CFD CAD model, tetrahedral elements for air and solid object, triangular for convecting surfaces, impose conditions, boundary and fan curves, rotational motion, ambient conditions, create control volume, solve for this thing, post process result, temperature, velocity, pressure, heat transfer coefficients and all that. Advantage of this is things like temperature, then you have this pressure, then various H bottom, no, that small subscript, and then the what you call velocities and all. If they are inside the industry, inside your own thing, if they are catalogued and kept, two things, it is a must now, so that you can always work backwards and find out where the assumptions should have been wrong. Second thing is, if in a similar configuration you can directly use them 1:1. So, I will withdraw the earlier remarks I have made saying there are no equations which will solve your problems. These equations will solve your problems, but they are not easily available, and they are all valid only for this physical configuration, the model geometry. So, if a similar model geometry is there, and if you know the amount of shielding and all that, so you will be able to continue with it. So, we have all these things saying what is the natural or forced architecture. I will come back to it, saying intake and exhaust path, ambient temperature range. We have this, I mean at least I had, no, because I come from a beautifully almost air conditioned environment. Our temperature rarely, even in the what you call winter, it goes below I think 13 degrees Celsius, and in the summer at least in the places I know, it has rarely hit a few degrees above my skin temperature, maybe around, skin is body is 37, skin may be around 35, around 40. So, 15 to 40, in fact it is centered very much around the ideal 24 degrees, it is a real beauty. You have seen that, no, it is a beautiful temperature in which we work. But outside, ambient temperatures, especially in some places, vary tremendously. Diurnal, in a day itself, things hit very low temperatures and hit very high temperatures, especially in desert conditions. And when you come to the seashore, only thing that seems to, the temperature is fairly stable, but the humidity is ridiculous. It is really ridiculous. It is in fact it is very easy for us to create drinking water, that is you take any condenser and the water will be freely coming out of the AC condenser. You collect all that water and then typically that is much better than any commercially available demineralized water. It is recycled and used for filling batteries. That much of humidity is there all around. And the place where I am talking from, we are notorious for being the heat and dust people. I too do not know how I am survived. I am very sure there is some being somewhere taking care of me. There is, the quality of air is not very good, and some of the places where your electronics cabinets work, they are in very harsh environments. They are not benign environments anymore. If you go to the shop floor, you also have, other than the things what I am talking about, whenever you have fluids, cutting fluids and all that, besides the humidity, sometimes you have other materials. Typically in our case, we have a grinder, so that grinding dust is there in the air all the time. So, in spite of having the best what do you call vacuum device which goes collects it, we have a cyclone collector and all that, still all around you can have the dust. And if you are working in a mill, to us it looks like a bakery is a very simple device, no? All you do is get some dough and then you nicely make it and then allow it to rise, and then you make beautiful bread. We live by bread. The reality is handling the dough and all that, no, it is full of dust, and we have equipment very close to them. Of course, we need not talk about other industries like the cement and coal and other places where quality of air changes there. The advantage for it is we know about it, hence you deal with it. Places like what we think labs and all are benign places, still things exist, and then we have intake and exhaust paths. We have a little bit of control on the exhaust. The intake, we are not very sure about it, where it comes from. Noise levels, then something which we come with push pull. It looks very easy, just put a exhaust fan in a room. In a room exhaust fan makes sense, but inside an equipment and all that, something which blows air in the direction we want seems to be much better. So, a push air thing seems to be better because we know where to push the air to. And if we just put an exhaust fan, chances are circuit will be, in spite of the best attempt to make the the what you call air flow around wherever you want, it will find a leakage path, short circuit itself, and it will go away. So, beautiful noisy exhaust fans, clogged filters and hot equipment. So, somebody has to work about the push pull or push pull configuration, ambient temperature ranges and humidity ranges. This is where important thing is, in the case of highly humid and condensing type of environments, peculiarly air is heated. You would have seen, if you are an automobile, normal driver, you see that we have a windshield or a windscreen, and then there are vents down, and when it rains, you will notice that all the things, everything seems to be condensing on your windshield. Sides you can ignore. So, they have hot air which is blown inside, and the beauty is it works only if you heat the air and also run the air conditioner, because the air conditioner when you run, when the cold air hits the air conditioner evaporator, lot of the heat condenses and comes out. So, you invariably dry the air, and in the case of naval and what do you call shore mounted equipment, there are also duct heaters, and I have given you an example of the domestic refrigerator. It is a must to heat the side walls of a refrigerator now, because any condensation that takes place inside, because generally you do not live with you do not enjoy living in a room which has 40 degrees centigrade. So, ideally I think people enjoy around 22, 23 degrees. At that point if it is humid, water will start condensing on the sides of the refrigerator, and if you take the old type of mineral wool insulation, soon the insulation gets waterlogged. Even in spite of your having a best what do you call polyurethane formed in place insulation, still condensation is real. So, they have found out a much easier way. So, they run the that what do you call condenser coils inside, and which has a double thing. You have much more area for the heat to spread, and it also aids in the anti-condensation. So, we have this stuff about how to control the quality of air. You remove dust, you control humidity. Similarly, you control the temperature intake and this thing, and then something which we do not like is the noise levels. Yep, things are noisy, much more noisy. So, I have been endowed with hearing aids. For me, it is a matter of switching off the hearing aids, but for sensitive people who are trying to sleep, noise is noise. And same thing in the case of our what do you call equipment racks. If all the racks start making noise, we have a problem. And further, it is not well known that all the fans run about the same temperature, and all the equipment, the fan cooling devices, similar ones run all about the same speed, and you have a beating effect. Imagine a fan which is running at typically I think they all run around 700 rpm, low speed is around 700, high speed is around 1400. So, imagine there is one or two devices running at 700 rpm and some other devices running a little higher or lower. So, all the sounds beat together and unintended, we cannot even predict where the sound is coming. You have multiple harmonic beats riding all over the things. So, that is reality. So, somebody has to work about this. Something very related is this power budget, saying do you really have that much power to afford the luxury of playing around the cooling. Then servicing. I told you about how to remove those filters and then take them out. Usually they have spares, they put it in place so that the mean time to repair is minimized, and depending on the conditions and depending on the logging of the data, they have a servicing routine. So, I was only talking to you about how to clean the air filter. So, it is with inside also you have so many dust and other things which are real. You have seen this? Ha ha ha, experience is at a premium. If you make something general, it is only valid to that particular experience. You cannot generalize across this thing. So, there is no way of extrapolating, maybe a little bit of interpolating can be done. So, develop engineering rules to evaluate equipment design. So, engineering rules could be total cross section, total volume, total heat generated, and typically the range in which you have to adjust your cooling technique. Have an idea of answers before experimentation. I think you know about it. These days with the internet, they will put somebody and then write somebody else saying something somebody said like that. There is no internet. So, if they show Abraham Lincoln or if they show others saying internet, do not waste time in internet, you know who said what. Thing is, check up about it, saying if you have a good theory, it avoids unnecessary experimentation. Please check who said it and then check again and again, and snopes may or may not help. So, the thing is, if you have a reasonably good theory and some little bit of model saying this, because of the engineering rules already we have saying, if you follow this, if you have this much of volume and all that, unnecessary experimentation can be avoided, and almost first time the first run you are very close to the answer. If you are making a what you call little next run, you can do, then what you call, you can optimize it, implement recovery from single point failures. So, we know what caused the failure, so you can probably try to improve things from there. I will try to see, I will try to understand these fans which I have come across agreed earlier. I have told you why I am saying is, you can go to several what do you call fan manufacturers. Typically the fan manufacturers give this type of a curve. What causes this is not my concern. You see, here we have a peculiar dip in it, and then the subsequent lectures talk to you about how an unstable region is produced. So, we have here radial impellers, you have seen here. So, the air is enters here, air goes away. So, again here you have so many things saying forward and reverse when, pointing fans. The advantage is pull systems due to natural 90 degrees turn. So, if you mount it on the roof of an equipment, it blows everywhere. So, there is no curve inside, there is no elbow which is taking the air. So, you must have seen all those whirly bird antennas on several roofs. Advantage of whirly bird is naturally there is something which is rotating, air starts exhausting. Both versions are there. There is one which is helped by a small built-in motor, there are some which are motorless. As the air from outside comes, it acts like a natural what do you call windmill. Yes, I too had the doubt. A windmill impedes the airflow, but then at the bottom you already have warm air rising. So, that is how a whirly bird works. But this is very low, this sort of, if you see a fan like this, typically average they are only about 80 mm. So, you have about 100 mm also, and then width you have starting from 250 mm, then 300 mm. So, you have 300 mm by 80 mm, beautiful circulators are available, and then you see here it has probably a built-in motor inside, and then if those pictures show, it also shows a rotation of the thing. In this case, the vanes seem to be curved backwards. I will stop it here. The thing is, pressure capabilities, for example, static pressure itself is twice as much. If you have a typical impeller radial fans, and then you have a reasonably straight curve compared to this. The advantage of it is using what you call similar power capabilities, but the cost is very high and the power also is maybe 2 times as much, because it is a product you have, while this fan ideally works in this region, this into this fan can work in a very wide region, that much. So, total area under this is approximately 4 times as much. Only problem is fan spacing is limited due to the flow path. So, you cannot cascade them, you understand, you can't put one more, but if you have this axial blow fan, you can put one fan, another fan and so on. Actually, you can build up the pressure. In this case, it is not simple to make anything out of it. Allow me to just go forward, because I do not remember how to measure system resistance, right fan and operating. Yes, good. Now, our problem is, how do you decide 2 things? This is a typical something which we understand very easily. Typically, this is a load curve. So, as we know, if you increase the voltage, current will increase. So, let us say you have a source here. In this case, we have a voltage and what do you call this thing, and the current here. It is very easy. As you increase the voltage, the current comes down and so on and all that. This is the total we are talking about. The magic is even our things work like this. Our own, if you remember that thermal, we had a electro thermal analog there. Similar thing works with the airflow systems. So, if you know the system resistance curve and if you know the fan performance curve, you know which is the operating point. This is what I keep harping about, saying this, a little of this curve you can get. This curve is valid because it is all taken under very specialized conditions. Understand, I do not know this bottom portion. A little of this is valid, a little of this is valid, but inside I am not sure whether it is valid at all anymore. And especially if you have a filter on this side, imagine you have an input filter, we still do not know how it works. Added to that, we come to the system resistance curve because of the tremendous variability in the geometry inside the system is not that easily estimatable. So, typically they have given how to build a device to measure a fan under test. You have seen this, no? So, change delta P from 0 by adjusting tunnel flow. So, we have various ways of measuring a plot here, measuring a plot here, and then try to find out the pressure difference across, no, which will give you something here, which will give you something here. Based on this, Q versus the small delta P can easily be measured. I will talk to you a little more about it. Saying another way of making it is, imagine you create a baffling section and you have an airflow sensor and a pressure sensor, and then you baffle it, increase and decrease. So, we know the airflow, we also know the pressure across that, and then you know the pressure from the inside this chamber to the outside chamber. So, the change in pressure versus the Q can easily be plotted out. The next picture talks about, see, while that is about the source curve, this talks about the system resistance curve. In the case of the system resistance curve, the equipment and the test is kept here and this fan is used to blow. In the other one, this fan is not used, it is only our other fan is there. In fact, it is removed. Here they increase and decrease the flow. So, we know the pressure from here to here, and then you can measure the total thing using, it is very easy to compute. If you know the orifice CD discharge coefficient and all that is easy to do. Now, we have a system pressure and we expect that if you put what you call superimpose one over the other, it is possible for us to find out which of the fans will work. So, operating point, low airflow, inefficient performance, high noise level, and then here low noise level because we have a fan which is there, and then in between, if you are not very sure about it, chances are multiple operating point, fan speed hunts between the operating point, which works a little even with our air conditioners. If you have 4 air conditioners in a room and 4 different thermostats, because air conditioner temperature is monitored as the inlet of the device, sometimes as the outlet of the what you call the evaporator. So, you see here the one which is set in a lowest or the highest cuts in and cuts out earlier, which will ensure that it keeps failing and somebody gets benefited by changing the fan. So, it is very much necessary for us to find out which is a good, though initial cost is high, overall we still have a nice margin to work with. So, can we simply increase airflow as power increases? What are the costs? So, the next slide talks about a summary of all these things. So, I will stop here for the while and We will continue in the next lecture with the slide which was stopped by, because it is a lot of this thing. So, we have all these fan laws from here and onwards. It talks about how to deal with forced convection and deal with actual air movers, fan movers, and general force convection. We already assume that the flow, how the flow is created is not that much of a thing, because that whole thing is held in a huge wind tunnel like device. That wind tunnel like device, we have full control about everything. Some of them are even closed circuit wind tunnels. But here we talk about a practical fan, often must be taken off the shelf. So, thank you. I will start in the next lecture about it. Thanks a lot.